Hello, hello, am I audible?
Yes, ma'am.
Okay, okay. So, good afternoon, everyone. I welcome you to the second problem solving session of NPTEL course Graph Theory. So, we'll start, we'll wait for 2-3 minutes and we'll start. We'll start after 2 minutes. Let everyone join the meeting. Okay, so let's begin. So, I hope my screen is visible.
Yes, ma'am. Visible, ma'am.
Okay, okay. So let's start. Let's recall what has been done. So last week we discussed Eulerian trail and Hamiltonian cycle. So let's quickly recall what was an Eulerian trail. So Eulerian trail, it was a trail covering all edges. It was a trail which was consisting of all edges of graph, and it has the same initial and final point. So basically an Eulerian trail was a closed trail consisting of all edges, and a graph with Eulerian trail was called Eulerian graph. And we had a nice, necessary and sufficient condition for a graph to be Eulerian, and it was that all the vertices should have even degree. And we also saw last time, like if a graph is Eulerian and if we want to find a Eulerian trail, we also had an algorithm, Fleury's algorithm, to find the Eulerian trail. So after Eulerian trail, we looked at Hamiltonian cycle. So Hamiltonian cycle was a cycle which was covering all the vertices of graph. And a graph is said to be Hamiltonian if and only if it has an Hamiltonian cycle. But the issue was, unlike Eulerian trail, there was no necessary and sufficient condition for a graph to be Eulerian. But we had some sufficient condition. We had a sufficient condition by Dirac's theorem that if the degree of if the set if we have n vertices in a graph, and if degree of each vertex was greater than equal to n by 2, then the graph has to be Hamiltonian. And we can see that this is only a sufficient condition. This is not a necessary condition. That is, if a graph is Hamiltonian, it does not imply that all the vertices will have even degree, because we can see in this, for example, this we can see we can see this graph, which is a C6, that is a cycle on 6 vertices. In this, degree of each vertex is 2, but degree of each vertex is 2, which is strictly less than n by 2 with 3. But this graph is still Hamiltonian, so we see that this condition is not necessary. But besides that, also in some of the exercises and in some of the lecture, we saw some necessary conditions for the graph to be Hamiltonian. First, for one of the this was one of the exercise, that if a graph is Hamiltonian, then the number of connected components after removing k vertices from that graph should be at most k. And we saw this last time. And this was a necessary condition. And there was one more. Then in the lecture, there was one necessary and sufficient condition for a graph to be Hamiltonian. That is, if we have two vertices u and v, and suppose uv is not an edge in a graph, but the degree of u, sum of degree of u and v was greater than equal to n, then G will be Hamiltonian if and only if G union that edge is Hamiltonian. So this kind of condition can be helpful to prove Hamiltonianness of a graph. So suppose you are trying to find a Hamiltonian cycle and you are able to find a open Hamiltonian trail. That is you are able to find a path which is covering all the vertices, which is starting from say u1 till uk, and it is covering it is a trail which is covering all the vertices, but there is no edge between u1 and uk. Then you check if degree of u1 and degree of uk is greater than equal to the number of vertices. And if this condition is satisfied, then you can conclude that this graph will be Hamiltonian. So this is one of the conditions. Like if you want to show some graph is Hamiltonian, you can look at this condition. And moreover, using this, then we can have another condition that G will be Hamiltonian if and only if closure of G will be Hamiltonian. And closure of G was defined as, given a graph G, if u and v were vertices and u and v was not an edge, so we were reclusively adding all the edges whose degree sum of the two was greater than equal to the number of vertices. So this was about Eulerian trail and Hamiltonian cycle. So now let's look at some questions. So first question is this: let KMN be complete bipartite graph. So we know before the questions, this sorry. So what is a bipartite? Now during this week we studied bipartite graph. So what is a bipartite graph? A bipartite graph is a graph whose vertices can be divided into two sets A and B, such that any two vertices in set A does not have an edge and any two vertices in set B does not have an edge. That A and B are independent, or in other words, we can also say that a graph will be bipartite if we can divide the set of vertices in two sets such that if we have any edge in G, one vertex has to lie in A and other vertex has to lie in B. So this is what is a bipartite graph, and we have a necessary and sufficient condition for a graph to be bipartite, and a graph is bipartite if and only if it has no odd cycle. So if you want to disprove some graph, if you want to show that some graph is not an bipartite graph, it is sufficient to find just an odd cycle. If you can give an odd cycle in a graph, then you can directly conclude that that graph won't be bipartite. So here are some examples of bipartite graphs. So here you can see all the edges are growing from any edge in this graph has one vertex in A and one vertex in B. So this graph is a bipartite graph. And also you can see that any even cycle, C2n, where C2n is a graph of cycle on 2n vertices, any even cycle graph is a bipartite graph. So this you can directly conclude from the theorem, or also you can give a bipartition, or you can directly give the bipartitions, and you see that C2n will come out to be bipartite. And suppose we have a graph G, we have a notion of complete graph. A complete graph is one in which any two vertices are adjacent. So for bipartite graph also we have a notion of complete bipartite graph. So if we have KMN, a complete bipartite graph will be a graph on m plus n vertices, where A will have m vertices, B will have n vertices, and we can have all the possible edges going from A to B. That is, any vertex in A is attached to any vertex in B, but there are no edges within A or B. So this is a complete bipartite graph, and here you can see an example of K23. A has two vertices, B has three vertices, and we have all the possible edges which are going from A to B. Hence, it is a complete bipartite graph on 2 and 3 vertices. So now, let's look at the first question. So we have just defined what a complete bipartite graph is. Now additionally, let's assume that this complete bipartite graph is Hamiltonian. Then the first question is, what should be the sum of m and n? So what do you think? If Kmn is a complete bipartite graph and we are assuming Kmn to be Hamiltonian, then m plus n should be odd or even. Any answers? So we have that.
Even
Yes, even. Can you tell why it is even?
because that condition is there no sufficient condition for Hamiltonian. Every vertex should be even.
Oh, oh, that is every vertex should be even. That is a condition for Eulerian graph. We are assuming that this is a Hamiltonian graph. So necessary and sufficient condition for Hamiltonian graph is that. So we don't have any necessary and sufficient condition for Hamiltonian graph. So it is not necessary that all the vertices in an Hamiltonian graph should be even, or it isn't sufficient also. So that is, so first of all we are given that Kmn is a bipartite graph. Any other answer why m plus n should be even?
If, if m plus n is odd, then odd cycle will be formed.
Yes. Then what is the problem with the odd cycle?
If it is odd cycle, then okay. Then
Yes,
it
you
is not a bipartite, no?
yes. So you are, so since Kmn is a bipartite graph, from the necessary and sufficient condition we know that all cycles in Kmn should be even, should be of even length. And we are also assuming that Kmn is Hamiltonian. So if Kmn is Hamiltonian, then what is the definition of Hamiltonian graph? So if Kmn is Hamiltonian, then we can guarantee a cycle of how much length? If Kmn is Hamiltonian, so Kmn has, this has m plus n vertices. This graph has m plus n vertices and this graph is Hamiltonian. Therefore we have a, if it is Hamiltonian, then we have a Hamiltonian cycle.
Hmm.
And if we have a Hamiltonian cycle, what will be the length of this cycle in Kmn?
M plus n minus 1.
Y minus 1. So suppose, see, you have suppose 3 vertices. So the cycle has length 3, right?
Yes.
Yes, right.
So
Sorry.
yeah, you're right. So if we have a, so Kmn is a bipartite graph, so all cycles should be of even length. Now Kmn is Hamiltonian, therefore we have a Hamiltonian cycle consisting of all the vertices. And how many vertices we have? We have m plus n vertices. Therefore m plus n should be even. So is it clear to everyone why m plus n should be even? So we get that this answer is even. Okay. So now the next question is K24. Is K24 Hamiltonian? So what is K24? First of all, K24 is this. We have so k to 4, by k to 4 we means that set A has 2 vertices, set B has 4 vertices, and we have all the possible edges going from A to B. So this vertex will be attached to each vertex, and this will also be attached to each vertex. So what do you think? Is this graph Hamiltonian?
Yes, ma'am.
Why?
Because it 2 plus 4 is 6. No, it is even.
Yes, but see, here this is just a so yes, this is a so we know that m plus n should be even. So this is a necessary condition, but this is not a sufficient condition. So here we have just got that if KMN is a bipartite graph, then m plus n should be even. But we haven't shown that if m plus n is even, then KMN should be Hamiltonian, right? So we cannot conclude this from part A. If this is Hamiltonian, we'll have to find a Hamiltonian cycle, or to conclude it in some different manner. Do you understand why we can't conclude from part A?
Yes, yes.
Yes. So now, okay. So now once we can't, for this question we can't use part A. So tell now what is what do you think? Will this graph be Hamiltonian or not?
I'm not able to find any Hamiltonian cycle here.
Yes. Yes. So okay. So since let's okay. Yeah. So there's a possibility that this is not Hamiltonian then. But can you yeah, this won't be Hamiltonian. But now can you think of a reason why this is not Hamiltonian?
Because we have like on the right side we have four vertices,
Yes.
and if we are to cover,
Hmm.
like even if we start, like even if
Hmm.
our first vertex is from the set on the right,
Yes.
and yeah, so like even if we take all the possible routes,
Hmm.
we cannot cover all six vertices without crossing at least one of the two vertices on the left twice.
Yes, yes, yeah, very good. This is right reason. So what she is saying that suppose we want to construct a Hamiltonian cycle. Suppose we start from right. Suppose we are starting from V3. Then since it is now we have to show that it is Hamiltonian. We have to find a Hamiltonian cycle which is covering all the vertices. Now we pick a vertex from set B. Now the other vertex will have to be from set A. It cannot be from set B itself because there are no edges within B. So let's say it is V1. Now the next vertex will be from set B. Say we are taking V4. Now the next vertex will be from set A, say V2. But now after the yeah, V3, V4, V2, and now let's say we take V5. But now after this step, so after this step, so we have covered this vertex V1, V2, V3, V4, V5. But now we have to connect V6, but we won't be able to do it because there is no edge between V5 and V6. So we see that we cannot construct a Hamiltonian cycle here because we have to alternate. If we have to construct a Hamiltonian cycle, we have to alternate between the vertices of A and vertices of B. So if m is greater than n, then we cannot construct a Hamiltonian cycle because if it so if any so if it is a Hamiltonian cycle, say V1, suppose we have a Hamiltonian cycle from W1 to Wm plus n. So so all the vertices should be alternating. So our first m so W1, W3, and so all the odd vertices should come from set A and all the even vertices should come from set B. And we know that m plus n is even. So if m is greater than n, this complete bipartite graph cannot be Hamiltonian. So do you understand like why this graph is not Hamiltonian?
M is less than n, no, here.
Oh, okay. Yeah, if m is greater than n or m is less than n. In any of these scenario, if we cannot have in both the here m is less than n. Yeah. But you can but this is a graph. So like you this graph will be isomorphic to if you take these vertices in so this is kind of a symmetric thing. So if kmn is not bipartite, then if kmn is not Hamiltonian, then knm cannot be Hamiltonian either, because they are isomorphic. So we see that if m is greater than n or m is less than n, then this graph cannot be Hamiltonian. So does everyone understand this?
Yes.
Yes.
And if it is equal, then it is Hamiltonian. If m is equal to n,
Yes, exactly. This is the next question. Can we put some condition on m and n for kmn to be Hamiltonian? So from B part, we have got that if m is greater than n and if m is less than n, then that's kmn cannot be Hamiltonian. So what about if m is equal to n? Can we then say that if m is equal to n, is kmm, then if m is equal to n, then this become kmm. Is kmm Hamiltonian? So what do you think? So suppose first I take m equal to 2. My graph will look like this. I have to take this and this. So is this graph Hamiltonian?
yes.
Yes. So what will
Yes.
be the cycle? So if I label the vertices, our cycle will be V1, V2, V4, V3, V1. So we see that this is coming out to be Hamiltonian. So can we generalize this? Can we say that
Yes.
KMM will be Hamiltonian?
Yes, KMN will be Hamiltonian if m is equal to n,
Hmm.
and not Hamiltonian if m is not equal to n.
Yes. Yes, very good. Yes. That's right. So does everyone understand why? So see why KMM will be Hamiltonian, because so our set A will have some vertices, say V1, Vm, and our set B will have some vertices W1, Wm. Now since this is complete bipartite graph, V1 is attached to any of the vertices in set B. That is V1 W1 is a edge, V1 W2 is a edge, V1 W3 is a edge, and so on. So we have all the possible edges now. So now we can see V1 W1, V2 W2, VMWM, and then again to V1. This will be a Hamiltonian cycle. So we have shown that if M is equal to N, KMN is Hamiltonian, and if M is greater than N or less than N, then it is not Hamiltonian. So is first question clear to everybody? Yeah. Yes. Is there any question?
Ma'am, can you please explain that m plus n should be even, that part, ma'am?
Okay. Yeah, sure.
Thank you, ma'am.
So yeah, why first, so we have that kmn is a so kmn is a bipartite graph. So necessary and sufficient condition for bipartite graph is that all cycles in kmn should be of even length. Is this fine? This
Yes,
is
ma'am.
fine.
Yes, ma'am.
Huh?
Yes, ma'am.
Yes. So now in additional to assuming that, we are also assuming that kmn is Hamiltonian. And what do we mean by Hamiltonian? If a graph is Hamiltonian, that means we have a cycle which is consisting of all the vertices. Now this kmn graph has m plus n vertices. Why? Because kmn is that set A. Kmn, by kmn we mean that set A has m vertices, set B has n vertices, and we are attaching all possible edges going from A to B. So we see that kmn has m plus n vertices. And since Kmn is Hamiltonian, that means that we have a Hamiltonian cycle consisting of all these m plus n vertices. And a cycle of n vertices is of length n. Therefore, we see that we have in this Kmn, we have a cycle of length m plus n. But since the graph is bipartite, all these cycles should have even length. Therefore, m plus n should be even. Now is this clear?
Okay, ma'am. Clear, ma'am. Clear. Thank you, ma'am.
Okay. Yeah. Any other question from question 1? Okay. So let's move on to next question. Now, question 2 is that we have a graph with 20 vertices. Delta V is 10, that is maximum degree is 10 and minimum degree is 9. Then we have to see if G is connected. So this is a particular case from one of your practice problem. And the answer was like if G is connected. So have you tried this question, and does anybody has a reason why G will be connected? So we have a graph with 20 vertices, maximum degree is n and minimum degree is 9. So suppose first of all since maximum degree is 10, so let V1 be a vertex of maximum degree. That means V1 has degree 10. Therefore, that means that V1 is attached to 10 more vertices. V2, V3, V4 till V11. And total vertices are 20. So, we have 9 more vertices remaining. V19, V20. So we see that we have these so we have V1, then we have these 10 vertices which are adjacent to V1 because V1 was a vertex of maximum degree, and then we have these other 9 vertices which are not adjacent to V1. So we have to show that G is connected. So to show G is connected, we'll show that V1 can to show G is connected, we'll show that there's a path between V1 and every other vertex. So if we talk about V1 and V11, so we have a path V1 and Vi, where I is belonging to 2 to 11. Since these are adjacent, so we see for them this condition is satisfied, that we have a path from V1 to Vi for V. But what about other vertices? Suppose we pick a vertex V5 which is not adjacent to V1. So from the given data, that minimum degree is 9. That means each vertex should have degree at least 9. And maximum possible degree is 10. So from this given data, can we find a path from V1 to V15? So we know that degree of V15 is greater than equal to 9 because minimum degree is 9. And these are 9 vertices. So now can you see why there will be a path from V1 to V15? So to
Yes,
show,
yes.
yes, okay.
It will,
Yes, which
yes,
part?
it will be connected to V12, V13, 14 up to V20, and one more edge will be connected to some other in V2, V3 or something. So obviously it will be connected a path via V1 to V15. There will be a path.
Yes, very good. So what he is saying that since degree of V15 is greater than equal to 9, and in this set you see in this set you see these are 9 vertices. So if degree V15 is greater than equal to 9, so there is at least one vertex from V2 to V11 which is connected to V15. Because if none of these vertices, if none of these V1 till V11 are connected to V15, then V15 can be connected to at most remaining vertices, which are 8. But we have been given that degree V5 is greater than equal to 9. Therefore, V15 is adjacent to at least one vertex in V2 till V11. And suppose that is Vk. So we see we have a path V15 to Vk to V1. So we see we have a path between V1 and V15. And similarly we can show that there exists a path from V1 to Vm where m is between 12 to 20. So V1 was already connected to V2 and V11, and we can find a path from V1 to the remaining vertices also. So from this we can conclude that G is connected, because we can connect any other vertex, because we can connect all the vertices from V1. So now if we pick, so V1 can be V1, we have a path from V1 to any other vertex. So if we pick any two vertices, say Vm, Vn, so we have a path from Vm to V1, and we also have a path from V1 to En. So we see that any two vertices can be joined via V1. Therefore this graph will sorry, was there a question? Hello. So I was saying that we can see that, and if we pick any, so first we showed that V1, we have a path from V1 to the remaining to all the remaining vertices. Now to show that G is connected, we want that if we pick any two vertices, there should be a path between them. So if we pick Vm and Vn, from the part we have already proved, so we have a path from Vm to V1, and we also have a path from V1 to Vn. So if we adjoin these two paths, we get a path from Vm to Vn. Therefore we see that this graph will be connected. So is this question clear?
Yes, ma'am. Clear.
Clear? Okay. And you see, and you can see that this was just numbers. The general case will also follow similarly. So you just have to count the vertices which are adjacent to V1, and you have to count the vertices which are not adjacent to V1. And using this similar argument, you will be able to show the general case. And you'll see that this graph will turn out to be connected. So now next question. We start with a connected graph G. Then V is called a cut vertex of G if G minus V becomes disconnected. So what is a cut vertex? Suppose we have a graph like this. So this graph is connected because we have between any two vertices there is a path. This is G. But we see that G minus V G minus V becomes this. G minus V becomes disconnected. So in this case, V is a cut vertex. This is similar to a question that we discussed previously. There we had a cut edge. Now instead of edge, we have a vertex. So this is a cut vertex. Now what we have to do is that, so we have to prove that if G is a connected graph and V is a cut vertex of G, then G bar minus V is connected. G bar minus V is connected where G bar is complement of G. So first of all, we have a cut vertex V, and then we have, so suppose for time being, let's assume we have two components. So this is a graph G. Assume G bar minus V. Assume G minus V has two components. So now if V is a cut vertex, so we have this case. So if V is a cut vertex, what we have that if we remove V, then this graph become disconnected. That is, it will have two components, C1. So first we are assuming that it has two, suppose if a graph is becoming disconnected, that means it has at least two connected components. So first of all, assume like it has two components. So now we have to show that G bar minus V is connected. So what is G bar? Any VW, sorry, W1, W2 is an edge. So by complement we mean that W1, W2 is an edge in G bar if and only if W1, W2 is not an edge in G. So by complement we mean that the complement of graph will all have all those edges which were earlier not present in G. G. So now we have to show that G bar minus V is connected. So basically we have to show that if we pick any two vertices in G bar minus V, we can find a path between those vertices. So for suppose case 1, we have that x1 belongs to C1 and x2 belongs to C2. So can we say that we have, so do you think we have in G bar, do we have a path between in G bar do we have a path from x1 to x2? We have to show that G bar minus V is connected. So this so G was a graph in which V was a cut vertex. That is, after removal of V, this graph was getting divided into two components, C1 and C2. Now we are trying to show that G bar minus V is connected. So we have to show that if we pick any two vertices, we can find a path. So my case 1 is that I am picking one vertex from C2 and one vertex from C1. Can you see a path between x1 and x2 in G bar, complement of G? In G bar minus
No, we
V.
can't.
Yeah?
No, we can't. There is no edge.
Yes, there x1 and x2 is not an edge in G. That is true. You are saying that, right?
Yes.
So if x1, x2 is not an edge in G, what does it mean that it will be an edge in G bar?
Ma'am, x1, x2 is an edge in G. x1 and x2 is not an edge in G complement, right?
No. Why? So see, x1 is sitting here, x2 is sitting here, x1 is sitting here. So
Yeah.
So if there was a in G, if there was a edge between x1 and x2, then V won't be a cut vertex, right? Because we are given that V is a cut vertex. That means if we are removing V, uh, if we are removing V, C2 and C1 are C2 and C1 are different connected components. So if we had a edge between x2 and x1, after removal of V also it will be a edge. Then then these won't be two different components, right? So if x1 is
Oh,
in
okay,
C1
okay,
and
makes sense. Yeah, yeah.
so from we get that x1 is not an edge in G, therefore x1 and x2 is an edge in G bar, and therefore we see that we have we have a path between x1 and x2. Now what about the case 2? Suppose x1 x2 both are belonging to, suppose x1 x3 are belonging to C1. Now can we find a path between x1 and x3 in G bar? So since x1 and x3 are belonging to same component, there is a path between x1 and x3 in G. And from case 1 we have shown that if we have any vertex in C2, so we have from case 1 we have shown that if we have one vertex in C2 and one vertex in C1, they cannot x1 and x2 cannot be an edge in G, but hence it has to be an edge in G bar. So now we have that x1 and x3 are belonging to same components. Now can we find a path between x1 and x3 in G bar?
Yes, ma'am. Let us assume that there exists a vertex x4 such that there is no edge x1 and x4 and x3 and x4 in G.
Okay, yes. Suppose, so you
So,
are saying there exists V4 such that x1 V4 and
and
x2 x3 V4
before
are
does
not
not
in
exist in G.
G. Yes. Okay. Then we can, then yeah.
They're in G complemented.
Yes.
These edges.
Okay, yeah, this is fine. So if we can so you are right, if we can guarantee that there is a vertex V4 such that x1 V4 is not an edge in G and x3 V4 is not an edge in G, then we'll get a path x1 V4 x3 in G bar. But can you see from this given but this is true only if we can find such vertex which is not connected to x1 and x3. So in this graph can you see any vertex which is not connected to x1 and x3? Can you guarantee that any vertex here?
X2.
Yes, very good. Right. So we see that from case 1, x1, x2 and x3, x2 are not an edge in G. Therefore, x1, x2 and x3, x2 are in G bar, and hence we can find a path from x1, x2, x3. x3 is a path in G bar. So we see that if we have two vertices, one is coming from C1 and one is coming from C2, then we have a path between x1 and x2. If they are coming from same component, then also we have a path between x1 and x3. And similar, so and case 3 will be that x1 x3 are in C2. this will be same as case 2. So we see that if we pick any two vertices in graph G bar minus V, we can find a path. Therefore, we can conclude that G bar minus V is connected. So is this question fine?
This guarantees that no every vertex from C1 as the edge to every vertex in C2 in G complement, no?
Sorry, can you repeat your question? Yeah.
Every vertex in component C1
Hmm.
as a edge to every vertex in a component C2 in G complement.
Yes, yes, that is right. That if you have a, because yes, this will be a case. This will be case 1, right? If we have any, so any vertex in C1 is connected to any vertex in C2 in G complement. Yes, that is true. Yes. So what is your so you were asking if it is true or not only. So was this your question?
I got
Okay. Okay. So now before going to the next question, I want to recall the definition of diameter. So so what is a diameter of a graph? So diameter of a graph is maximum of DUV. So first of all, given any two pair of vertices UV, DUV refers to the length of shortest path between U and V, and diameter is maximum of all these length of shortest path. So this is what diameter is. So now let's compute the diameter for few easy cases. So is it clear that so k, let's first example is kn, that is a complete graph on n vertices. So is it clear why diameter of kn will be 1? So I've also so first is complete graph. So I've also written the reason. So in complete graph, if we pick any two vertices v and w, vw will be an edge. So length of shortest path between any two vertices is 1, and maximum of all such length is also 1. So we see that diameter of kn will come out to be 1. Now second example is diameter of complete bipartite graph. So by complete bipartite graph we mean KMN. So KMN is a complete bipartite graph. So A has m vertices, m, and B has n vertices, wn. So can anybody tell that what will be the diameter of complete
2.
bipartite graph?
2. 2.
2.
So
Okay.
uh, it is 1 for if m is equal to n, and
Yes.
2 if m is not equal to n.
Yes. Very good. Very good. So we see that diameter of KMN is 2, because if d of VI is 1, if two vertices are in same bipartition, then their distance is shortest distance is 1, and if they are in different partition, then their shortest distance is 2 and maximum of all such length is 2. So we see that diameter of complete bipartite graph is 2.
only for case 1 mn is equal to how much? It will be 1, no?
uh
K1n.
yes,
K1n.
yes, okay, yeah, very nice, yeah. So he is saying that if we are taking k11, then diameter will be 1. Yes, diameter is 1. So this is for case when either m is greater than 1 or n is greater than 1. Yeah, right. Now the third is, what will be the diameter of C2n? So let's look at some particular example. First is C4. What is the diameter of C4?
2.
Okay, 2. Yeah, that is right. Because we see that these two vertices are adjacent, and this is uh, V1 and V4 have a common neighbor, so diameter of C4 is 2. Now if we look at diameter of C6, C6. So what will be the diameter of C6?
3, ma'am.
Yeah. So what will be the diameter of C6?
3.
3. Yes. So can we generalize it? What will be the diameter of C2n?
N.
Yes. Yes. Why? Because if we have this is the cycle, V2, V3, Vn, then Vn plus 1 till V2n. So we see that distance between V1 and Vn is n, and distance between V1 and Vn plus 1 will also so we have this cycle. So we see that all the shortest distances will be less than equal to n, therefore diameter of C2n will be n. So we see, let's see for V1 and Vn plus 1. So we can see this path is of length n plus 1, but this is a cycle. So if you look at the path V1, V2n till Vn plus 1, then this will have length n. So up till first n vertices, it has diameter less than n, and it has shortest distance between V1 and Vn was less than n, and after Vn also the distance is less than distance is less than n, therefore we see that diameter of C2n is n. And similarly, what will be the diameter of odd cycle? What will be the diameter of C2n plus 1? What do you think? So we have V1 cycle, we are going till Vn, then we have Vn plus 1, and we are going from V2n. So these are n vertices, these are n vertices. So and we have V2n plus 1. So what do you think will be diameter of this odd cycle?
N plus 1.
Yes. Yes. Yeah. So if we have 3, what is the diameter of C3? It is 2. And similarly, we can see for general case also the diameter will turn out to be n plus 1, because from V1 to Vn plus 1 we have length n plus 1, and the vertices after that will also have a length and will vertices after that also we will have a shortest path whose length will be less than n plus 1 by if we go via this way. So we see that diameter of C2n plus 1 will come out to be n plus 1. So all these 4 example for diameter fine? So this is n and this is n plus 1. Okay, so let's look at other questions now. Okay. Now, next question is, a graph is called semi-Eulerian if it has a trail covering all edges, but it is not closed. So basically, so our graph was Eulerian if we have a closed trail covering all edges. But by semi-Eulerian we mean that we have a trail covering all edges and it is not closed. So basically our initial point and so in the initial point and last point need not be same. Initial point and last point need not be same. So for example, if we look at this graph, this is a very simple graph. It is semi-Eulerian but not Eulerian. And we can look at other examples also, but the question says that if G is semi-Eulerian, then the necessary and sufficient condition for G to be semi-Eulerian is that it should have exactly two odd vertices. So how do we prove it? So we know that G is Eulerian if and only if all vertices are of even degree. Now we have to prove that G will be semi-Eulerian if and only if we have exactly two vertices which have odd degree. So suppose G is semi-Eulerian. That means we have an Eulerian, we have a trail consisting of all edges. So our trail is starting from U1, U2. So we have a Eulerian trail. So we have a graph G. G is semi-Eulerian. We have a graph G. So we have a graph G with, suppose we have a graph G and vertices with say n vertices, and we also have that G is semi-Eulerian. Therefore that means it has a trail consisting of all edges, but U1 UK is not an edge because it is semi-Eulerian. So that means we don't have that is we don't have same initial and final point. U1 UK is not an edge. So now U1 UK is not an edge, but then we see that G union, so we have this G union UK. So we have Eulerian trail. Now if we add this edge U1 UK, add this edge U1 UK, can we say that this graph will be Eulerian? We are given that G is semi-Eulerian. So
Yes, ma'am.
yeah, why it will be Eulerian?
Since U1 and UK are not connected by any edge,
Yes.
the degree will be odd at both vertices U1 and UK.
Hmm.
So we can't say that it is Eulerian. But if we have G union and U1 UK, it is Eulerian.
Yes. G union, but why G union U1 UK is Eulerian?
Ma'am, we will get odd degree at both vertices, ma'am, at U1 and UK.
But we need, yeah, this is what we are trying to prove, that U1
Yes,
UK
ma'am.
have odd degree.
Since
It completes the
there
cycle,
is
no, that's
Yes, yes. So
it
see,
completes the cycle.
yeah. So we are saying why G union U1 UK is Eulerian, because we have that U1 till U1 UK we were covering all edges. So this trail was covering all edges of G. Now G union U1 UK has one additional edge U1 UK. So we see that if we add this edge UK U1, then this graph, then we this trail is covering all the edges of the graph G union U1 UK. Is that right? Is this fine? That this U1 till UK was trail for G.
yes, ma'am.
Then this U1 till UK, and then this edge UK U1 is Eulerian trail, is an Eulerian trail for G union U1 UK. Sorry. This is an Eulerian trail for G union U1 UK. Now this graph becomes, so we see therefore that G union U1 UK is Eulerian. Therefore all vertices all vertices of G union U1 UK have even degree. In particular, degree of U1 and degree of UK is even in G union U1 UK. So since G union U1 UK was becoming Eulerian graph, we get that all the vertices will have even degree. So in particular, degree of U1 and UK is even in G union U1 UK. So what is the degree of U1 and UK in G? It is odd.
It will be odd, ma'am. Yes, ma'am.
Yes, because in G union U1 UK they have an additional 1 degree coming from the edge U1 UK. So in in the original graph G they will have odd degree, and all other vertices degrees remain unchanged.
Yes.
So we see that semi-Eulerian graph has exactly 2 vertices of odd degree. So is this clear? Is this question clear?
Yes, ma'am. Clear, ma'am.
Okay. So let's go to next question. Now we have that an independent set is a subset of set of vertices such that there is no edge between them. So basically we what is an independent set? Any subset of vertices, but no two vertices in that set are allowed to be adjacent. That is, no two vertices should have an edge between them. Then the question says that you have to show that a graph with diameter 10 has independent set of at least 6 vertices. So first of all, G is a graph with diameter 10. And diameter is maximum of distance of shortest path. Maximum of the shortest path between U and V. So if this is coming out to be 10, That means there exist two vertices u1 u v in G such that shortest path between them is 10. So let's list down that path. So if shortest path is 10, then u1 u2 till u10, which is equal to v. 4. Okay, like wait. Let's write it properly. So we have u, then we have u1, u2, u3, u4, u5, u6, u7, u8, u9, u10, which is just v. So we have that this is the shortest path between u and v. So now we have to show that this u10 is equal to v. Now we have to show that this graph has independent set of at least 6 vertices. So basically you have to give me 6 vertices which have no edge between them. So can you, with this data that this is the shortest path between u and v, can you give me 6 vertices which are independent?
Ma'am, U2, U4, U6, U8 and U10, ma'am.
U, U2, U4, U6, U8 and U10. Okay. So why? First, why? Why there is no edge between U and U2? Why this? Why are you? So you are giving this set. So, but why this set is independent? To show that this set is independent, we have to show that there cannot be any edge between these vertices. So, why can't there be a edge between u and u2?
Ma'am, because all these vertices are adjacent to like the
No, ma'am. Then the
odd
diameter will
vertices.
reduces. And the diameter will reduce from 10. If there is a path between u and u2, then the diameter will not be 10.
Yes, the duv won't be 10. That is, so we are taken, yeah. So we know that shortest distance between u and v is 10. So if there is a path between u and u2, then we are getting a path of length 9 between u1 and u10, right? We can go to u2 and then we go along same path. This path is coming out to be of length 9, but we have assumed that shortest path between u and v is 10. Therefore we see that there cannot be any edge between u and u2. And similarly, there cannot be an edge between u and any of other vertices, and there cannot be any edge between any two vertices, because if there is an edge between any two vertices here, then we will be able to get a shorter path between u and v. That is a path of length less than 10, but we have assumed that the length of shortest path is 10. The length of shortest path between u and v is 10. Therefore, we'll get a contradiction, and hence this S is independent. So is it clear why S is independent? So is this question clear to everybody?
Yes, question is clear, but why it is said at least 6 vertices? Why it is not exactly 6? Why is it not exactly 6?
Uh, yes, because so this is just a part of a graph, right? So there can be, this is just a part of the graph. So there can be more vertices than these graph. This is not like, so this is a graph G. So this is just a part of this graph. There can be more vertices than this and more edges than this. We have just picked 2. So there can be more edges than these. There can be more vertices than these.
Is there any generalized formula to like find if n diameter is 9, then what is the at least number of vertices, something like that, in that independent set? Is there any generalized formula for that?
Oh, okay. I think we can generalize it. Okay. So see, yeah. So here we are saying that, so if diameter is coming out, so if we suppose, like, let's try, like, I don't know, but let's try to generalize it. Suppose diameter is 2n, then we are saying that, can we say that it has an independent set of at least n plus 1 vertices? I think this, yeah. So I'm just, so if you want to generalize it, I'm just like trying to generalize. So here n is 5 and we are getting that it has at least 6 vertices. So this should be true. We can generalize this. This should be true for this, I think. Yeah. So we use the same reasoning. So we have u, and then we have this u1, u2 till u2n v. So let's, if diameter is 2n, suppose the distance, shortest distance between u and v is
Here
2n.
vertices, ma'am. Here vertices are 11 and diameter is 10.
Yes, yes. In this case, in this case, in this path, the vertices is 11 and diameter is 10. Yeah, because see, so if you have to compute the length of path, so if you are going from u to u2, these are 3 vertices, but length is 2. So a path of length n has a path of length n has n plus 1 vertices. So if see, so this has 11 vertices, but the length of this path will be 10. 1 2, like if you count it, hence we have these 11 vertices. Like, was this your question, that why 11 vertices and length 10? Was this your question?
No, we are deriving that expression for no general.
Yes, yes,
You
yes.
wrote diameter 2n,
Yeah.
then independent set of at least n plus 1. So
Yes.
this is not that example, no?
Yes, yes. So I am generalizing it. Like, see, so here we had that, diameter was 10, and diameter was 10, and we were getting an independent set of at least 6 vertices, right? So this was 2 into 5. So I am, so in our generalization case, this is a particular example for n equal to 5, right? So if we want to generalize it, this can be, like, if you want to generalize it, this can be one of the possibility. Now we want to check that if this is true or not. Is this fine?
Yes, ma'am. No, it's okay. It's clear.
Okay. So now see, yeah. So here also you'll see that you can take, so we have to give n plus 1 vertices. So here you can see that we can take our independent set to be u2 till u2n. So you are getting an independent set of n plus 1 vertices. So this example can be generalized, that if diameter of graph is 2n, then it will have an independent set of at least n plus 1 vertices. So is this fine? So is this question fine?
Yes, ma'am.
Okay. Next question. Okay. So these are true false question. So first part is that every Eulerian graph with even number of vertices has even number of edges. So what do you think? Is it true? So we know that G is Eulerian if and only if all vertices are even. So first of all, let's write down whatever we know and then try to conclude if this is true. So every Eulerian graph with even number of vertices has even number of edges. So do we have, so first is that, what is so what is the relation between Eulerian graph and its vertices? That graph is Eulerian if and only if all vertices are of even degree. Now we have this vertices, number of vertices and number of edges. So is there any relation between number of vertices and number of edges in a graph? Or is there any relation between degree of vertices and edges?
Yes, sum of all the degrees is equal to 2 times edge.
Yes.
2 times.
Yeah. So we have that sum of all degrees is 2 times edges. So now the first statement is saying that every Eulerian graph with even number of vertices. So suppose even number of vertices has even number of edges. So from this formula, what will be the number of edges? Number of edges will be sum of all degree divided by 2. We know that, so which is basically, suppose this has even number of vertices, say 2n. So we have that dv1 plus dv2n by 2, and we know that all these dvi are even. So do you think that this so for a to be true, we have to we are saying that this term should always be even. So is it true that this should always be even? So we have that all these are even all these are even degrees, and we have even number of things. So if we divide them by 2, will we always get a even number? What do you think?
Ma'am, it says that, like, I mean, if G is Eulerian, all vertices are of even degree, then all of these vertices will have even degree, so their sum is even. So divided by 2,
Maybe odd, right? I'm not sure,
like,
but
it need not
maybe
necessarily
odd.
be.
Yes, yeah, it need not be necessary. So this statement can be false. So can we think, so from this directly we cannot conclude it is even. So since we from this we cannot directly conclude it's even, let's try to see if we can have a counter example. So because this sum can be, so basically, yeah, so see, if we so basically we to this for this to be even, yeah, so this need not be true. Now we are trying to construct a counter example. So we are given that we have even number of vertices. So if we take this degree sequence, say 2 2 2 2 2 and 4, if we take this degree sequence, so all are even degree, right? But number of edges you can see will turn out to be, if we add all these 2 4 8, number of edges will come out to be odd, right? Number of edges will turn out to be odd. So if we can construct, so if we can construct a graph with this, if we can construct a graph with this degree sequence, then we can say that this statement is false, because all the vertices are even, therefore the graph will be Eulerian, but number of edges are 7. So we just want to construct a graph with this thing. So let's try. So I think if we this we also discussed last time. So I think if we look at this graph, if we look at this graph, this has following degree sequence, right? So this has degree 2, this has degree 2, this has degree 2, this has
Yes,
degree
ma'am.
2, this has degree 2, and this has degree 4. And since all the vertices are even, this is Eulerian. But it has odd number of edges. So we see that first statement is false. Now let's look at the second statement. Okay. Yeah. So second statement say that every Eulerian bipartite graph has even number of edges. What do you think about that? What about Eulerian bipartite graph? Is it true for Eulerian bipartite graph? So let's look at this. Like so if it suppose first of all G is bipartite. So we can write vertices of G as A union B. And G is Eulerian. So what is the degrees? Total number of edges in this is dv v belongs to A plus dv v belongs to B. So we have that this is even and this is also even.
Divided
Sorry,
by 2,
this
madam.
upon 2. Sorry, this upon 2. Sum of all degree divided by 2. Oh, wait, sorry. So, what were you saying? Yes? So, we have that 2 times edges for bipartite graph. So, we are writing this same formula for bipartite graph. Now, we have that twice of edges is this. So, number of edges is sigma dv v belongs to A plus sigma dv w belongs to B by 2. Now can we guarantee that this quantity will always be even using some property of bipartite graph?
False, ma'am.
False. Why?
Even minus even, ma'am, equal to even, ma'am.
Yes. Yes, then why it is false? Sorry. So so is there any relation between, so if we are given that G is a bipartite graph, is there any relationship between sum of degrees of A, sum of degree of vertices in A and sum of degree of vertices in B? Is there any relation?
They are equal.
Yes, they are equal, right? So we see, so if this term is equal to this term, so this is basically 2 times sigma dv v belongs to A by 2. And this 2 and 2 get cancelled. So number of edges becomes this. And this is an even quantity. Because all vertices are even and we are adding even, so if we add some even numbers, we get an even quantity. So we see for Eulerian bipartite graph, we have that for Eulerian bipartite graph, the number of edges are even. Because we are using this property of bipartite graph, that sum of degree, total sum of degree of vertices in A is equal to total sum of degree of vertices in B. This is because any edge in a bipartite graph Any edge in a bipartite graph, say UV. If UV is an edge in bipartite graph, then one of them will belongs to A and the other will belongs to B. So any edge is contributing +1 to here and +1 here. So we see that total sum of degree of vertices in A is equal to total sum of degree of vertices in B. And hence, when we calculate, the number of edges are coming out to be even. So we see that B is true. Is this fine? Why B is true? Is everyone convinced that B is true? If
Yes.
there
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes. Okay. Good. Yeah. Okay. Now next question is, we have to find maximum number of edges for bipartite graph with 20 vertices. So first of all, tell me this. Yeah. So, yeah. So tell me this. If we have a complete bipartite graph on M and N vertices, what are the number of edges? Number of edges in KMN. Can anybody tell what is the
M into N.
M into N? Why?
Because
Yeah.
it's obvious actually.
Yeah.
You have
Why a number of edges in complete bipartite graph KMN is MN? What is so suppose VI belongs to A. What is the degree of VI? So this is A, this is B. So what is degree of VI? Or so why it is M, like even if you don't want to look at the degree, from this only you can see. So number of edges going whose one point is V1. We see V1 will be connected to each of the vertices in B. So number of edges starting with Vi is N. And similarly, V2 will be connected to all these edges. So we can see total number of edges in KMN is N plus N plus N plus N M times, which is Mn. So is this clear why in complete bipartite graph number of edges is Mn?
yes, ma'am.
So now
Yes, ma'am.
once we know this, now our question is, we have to find maximum number of edges for bipartite graph with 20 vertices. So order V is 20, G is bipartite. So first of all, so how do you suggest we find the maximum number of edges?
Like the partition K 10 comma 10 will have the maximum number of like by dividing it equally, like 20 vertices can be 10 10, then it will have maximum number of edges.
Okay, yeah. So first of all, what are the possibilities for order of A and order of B? So we see these are we'll have 10 possible like 10 or so. Let's see how many possibilities are there. So we can have 119. Yeah, we'll have 10 possibilities. 218, 3, 17, and so on till 10, 10. So basically we have that x, total number of edges are basically x into 20 minus x, where x is going from 1 to 10. And we see that this value is maximum when x is equal to 10. Therefore maximum number of edges will come out to be 100. So if you see, this will be the maximum thing, because if a and b have these degree and we are computing maximum number of edges, so we cannot have more edges than the complete bipartite graph. And we have from previous calculation we have shown that if a has m edges and b has n edges, then maximum number of possible edges are mn. So we see that a bipartite graph with 20 vertices has at maximum 100 edges. Oh, so yeah, has maximum 100 edges. So is this question fine?
Yes.
Okay.
Can you generalize this?
Okay.
If there are n number of vertices.
Okay, let's see. So if we have n number of vertices, so we have to see when this function is maximum, x into x minus n. So this function is x square minus nx. So we have to see that for what value of n this function is maximum. Sorry, for n is fixed, so we have to see for what value of x this function is maximum, where x is greater than equal to 0 and x is an integer, right?
I guess x should be n by 2. I guess.
Okay, let's see. So like this is bit analysis. So like, so we see, so if we have fx is equal to x square minus nx, if we look at the first derivative, it will come out to be 2x minus n. Yeah. So and see, so x, so when f dash is 0, x is n by 2. So yeah, this is fine. So if n is even, then we can say it is n by 2.
Yes, yes.
No, it is
Yeah,
x
sorry.
is n by 2, no?
Yeah.
Then it is n square by 4. The edges will be n square by 4.
Oh, yeah.
N
So
by 2
and
into n by 2.
yeah. So this so we have, so this function, if n is even, this function is maximum, attaining maximum at x equal to n by 2, and maximum number of edges will be
N square by 4
n by 2
into n by 2.
into n by 2, which is n square by 4.
4.
So yeah, we can generalize this. Okay. Oh. Now next question. Okay. So next question is, we have to compute diameter of Qn. So first of all, what is this graph Qn? So there are various way to understand this graph Qn. One of the ways that I like is this. So Qn, you can consider Qn is a graph whose vertices are given by subsets of this set 1 till n. So we see Qn is a graph whose vertices are given by subsets of this, and edges So A and B are two subsets of this set of n elements. There is an AB is an edge in Qn if A minus B, basically if A and B differ by one element. By one element. So this is Qn. So you see I have drawn two examples. So what are the possible subsets of 1, 2? So here you can see the possible subsets of 1, 2 are empty set, singletons 1, singleton 2 and the complete set. And there will be an edge if they differ, like if they have, there will be an edge between A and B if if the bigger set has exactly one more element. So we see that one, so empty set and one, there is an edge between empty set and the singleton and 2 and 1, 2 and this the complete set 1, 2 and 1 also differ by one element, so there is an edge. 1, 2 and 2 also differ by one element, therefore there is an edge, but there is no edge between the complete set 1, 2 and empty set because the difference of these two sets is 2 elements. So we are so in Qn the vertices are subsets of this set and there will be an edge if there is just one more if their difference is one more element. And similarly you can see the graph of Q3 also. So now we have to compute diameter of Qn. So can anybody tell what is the diameter of Q2?
2.
2. Why? Oh, so this is a simple diagram, so we can see that distance. So shortest distance between empty set and 1, 2 is 2, and any other distances is 1. So we see that diameter of Q2 is 2. So what will be the diameter of Q3?
It's 3.
3.
Why?
It passes through like every subset. For example, first it goes through like one subset, then it comes to the next, then it finally comes to null set. So based on the number of number of set, it will pass through number of subsets.
Yes, yes. So you are saying if we want to compute the shortest path between empty set and the complete set 1, 2, 3, and there is an edge only if there is a difference of one element. So if we have to construct a path, we can add only one element at one stage. Therefore we see that diameter of Q3 will turn out to be 3. And can you now generalize it? What will be the diameter of Qn?
N. It is N.
N. Because the shortest path between empty set and 1 to n will be n.
N.
and any other set, if we take a1 ak and a1 ak al, the so shortest path between these two. So basically I am saying this, if I have this set 1, 2, 3 and if I have other set is 1, 2, 7. So what is the shortest path between these two sets? So if I am looking at Q9 and if one of my element is the set containing these three elements and the other set is containing 1, 2, 3 till 7. So what will be the shortest path? What will be the length of shortest path between these two sets?
4.
4, because the difference of between these two sets are 4 elements. So if you want to add, go to a set with 4 more elements, and at one stage you can add only one element. Therefore you'll have to go at 4 stages, and the shortest path will turn out shortest path will have 4 length 4. So diameter of Qn is n because The worst case scenario is empty set and the complete set, and shortest length between these two sets is n. And if now we pick any other sets, the shortest length will come out to be less than n. So now is this clear why diameter of Qn is n?
Yes, ma'am.
Wait. Yeah. Yes. Okay. So, okay, there are other scenarios also. Okay, so see, 1 2 and 1 3. So this is this so this was so so we have checked that if we want to compute shortest path between A and B, and if A is a subset of B, then the shortest path is coming out to be order of B minus A. But what if A is not a subset of B? Suppose in this scenario, say 1 2 and 3. So what is the shortest path between 1 2 and 3 in this? So this is, oh, so sorry, I have done a mistake. So diameter of Q3 won't come out to be 3, because in this case, see, if you want to look at 1 2 and 3, if you want to construct a shortest path between 1 2 and 3, you have to go to 3 1 3 1 2 3 1 2 3 and then again 1 2. Okay, so but this is also coming out to be a path of length 3, so this is fine. Okay, sorry. Oh, okay, then it is fine. Okay, but I'm just saying that we also have to consider these kind of cases. That when one thing is not a subset of other. But they, okay, now see. So if we have A1, AK, and suppose we have B1, BK. So first we go to, basically we go to A1. So if we have, okay, so if we have two sets AB, first from A we go to A union B, and then from A union B we go to B. So this is the path. So and this path, shortest path here has ordered A union B minus order A. This is of length this, and this is of length order A union B minus B. Okay, so a diameter of Qn should come out to be n, but I think like we have, so I'll take this question next time, because I think there's something wrong with the proof that I was giving. So we'll discuss this next time. You can you can also think about this question till then. So now the last question is that if G is a regular graph and diameter of G is 3, then we have to show that diameter of complement of graph is 2. So let's do this question. So any idea how to do this? So first of all, we had this result that if diameter of G is greater than equal to 3, then diameter of G bar has to be less than equal to 3. So this was a result in one of the lecture. Is this fine? Yes. So now since the diameter of G is 3, so from this result we can conclude that diameter of G bar will be less than equal to 3. But now we have an additional condition that if G is regular, then diameter of G bar should come out to be 2. So this was also one of the question in your practice problem. So did you try this?
Yes, ma'am.
So okay. So first of all, diameter of G, since diameter of G is 3, that means there exist two vertices V and W who V and W in G who don't have a common neighbor in G. Is it clear why this is true? That since diameter G is equal to 3,
Yes, ma'am.
so we have two vertices VW whose shortest distance will be 3. So now if in G, therefore they cannot have a common neighbor. And we have already, so this is a result that we have already shown that diameter G bar is less than equal to 3. And now what, so okay, so if this is the case, so we have that VW shortest path between VW is 3, V2. And also since V1, and if we look at, this is G, and if we look in G bar, since there is no edge between V and W, this will be an edge. Now can there be a edge between V and V2 in G? This is the shortest path between V and W, and we see that there cannot be a edge between V and V2 in G, because if there is a edge between V and V2 in G, then we'll have a shorter path. So in G, since V and V2 cannot be a edge in G bar they will be an edge, and similarly they will be a edge in V1W will be an edge in G bar. Now in G bar, what is the shortest distance between V1 and V2?
2. 3. V1 and V2. 3.
According to this it is 3, but there can be other vertices also. So we can say that it will be greater than equal to 2, because there is not an edge between V1 V2, because there might be some other vertex here V1 and V2 can have a common vertex because this is just a part of graph. But we can conclude this much, that their distance has to be greater than equal to 2 because V1, V2 is an edge in G. So they cannot be an edge in G bar. So we see that their shortest distance has to be greater than equal to 2. Right? So we see that diameter of G bar is also greater than equal to 2. But from this result we know that if diameter G is greater than equal to 3, then diameter G bar is less than equal to 3. And we have to show that if G is regular, then diameter G bar is 2. So suppose diameter G bar, we are proving it by contradiction. Suppose diameter of G bar is not equal to 2. Therefore, there is just one possibility, that diameter of G bar has to be 3. Right? Because from this result, we have that diameter G bar should be less than equal to 3. And we are assuming diameter G bar is not equal to 2. So there is just, and diameter G bar has to be greater than equal to 2. Therefore, we see that there is just one possibility for diameter G bar, which is 3. Now to prove this result, we just have to arrive at some contradiction. Because we are assuming that diameter G bar is not 2. So now we have that this is VW. Now if diameter of G bar is 3, so we can do the same thing in G bar also. That is, we'll have two vertices XY in G bar, XY in G bar whose shortest distance is 3. DG bar in XY has distance 3 and DG VW is 3. Now to arrive at contradiction, we'll show this, that degree of V plus degree of W is not equal to degree X plus degree Y in G. So if we show that these two things are not equal, then we are done. This is our claim. Why we are done? Because we have assumed that G is regular. If G is regular, in G all vertices have same degree. So this sum should come out to be equal. But if we are able to show that the LHS is not equal to RHS, then we have arrived at contradiction, and therefore this assumption that diameter G bar is not equal to 2 is false, and we get our result that diameter G bar is equal to 2. So till now is everything clear, that if we prove this claim, then we are done. So is it clear till this step? So I am saying that, so we have been given that diameter of G is 3 and G is regular. We have to show that diameter of G bar is 2. Now from this result we know that if diameter G is greater than equal to 3, then diameter G bar has to be less than equal to 3. So we are proving this by contradiction. So we are assuming, so we have to prove that diameter G bar is true. So we are proving by contradiction. So we are assuming, suppose diameter G bar is not equal to 2. And if diameter of G bar is not equal to 2, then there is just one possibility for diameter G bar. That is, it has to be 3. And if the diameter G bar is 3, then we can find two vertices X and Y whose shortest path, whose shortest path length is 3, and X and Y are those two vertices. So now if we show that sum of degree of V and W in G is not equal to sum of degree in X and Y, then this cannot happen. They have to be equal because G is regular. So if we show this, then we have arrived at contradiction, and hence our this assumption that diameter G bar is not equal to 2 was wrong. So my question is this clear that if we prove this claim, our proof is done? We still have to prove this claim. Okay. Hello? Hello? So is it clear up till now?
Yes, ma'am.
Okay. So let's prove this claim. So V and W are vertices which have shortest path shortest path of length 3 in G. Sorry, yeah, VW has shortest path of length 3 in G. Therefore, V and W have no common neighbors. In G. And XY were the vertices. So suppose V, W, XY. These are the 4 vertices. Now first of all, we are looking at all the possible connections in G and G bar. So V and W has shortest path of length 3 in G, and XY has shortest path of length 3 in G bar. So now V and W is not an edge in G because their shortest path is 3. So we see that V and W will be an edge in G bar. And similarly, XY has shortest path of length 3 in G bar. So XY is not an edge in G bar. So XY will be an edge in G. And now, yeah, also now what about V and W? So, yeah, we have, so now we have this XY. XY has shortest path of length 3 in G bar. Therefore, we say that, therefore, if we have any vertex V, so now now XY don't have a common neighbor in G bar. So we have that either XV is, so XY does not have a common neighbor in G bar. So we have that can XV there can both X, so yeah, so we have this scenario. Suppose yes, wait, XY has shortest path of length G in G bar. So we have no, V and W have no common neighbors, and if we have any vertex, so we see that if we have this V vertex, it has to be attached to either X or Y in G, because if V is not, so I am saying it, so if X has to attach to V or W, so X, because if XV and XW is not an edge in G, if xv and xw is not an edge in G, then xv, xw, if xv and yv is not an edge in G, then xv and yv is an edge in G bar, but length of shortest part between xy and G bar is 3. So we see that this v has to be connected to either x or y. So suppose v is connected to x, and similarly either xw or vw is an edge in G. But because xv, we have already assumed that xv is an edge in G, xw cannot be an edge, because uh, then v and w will have a common neighbor. So this is the only possibility. So we see that in G this is the only possibility. And now xw cannot be an edge in G, so xw will be an edge in G bar, and vy is not an edge, vy cannot be an edge in G, so vy will be an edge in G bar. So we see that these four vertices can have only this possible relation between G and G bar. So now if we take our set S to be all the vertices minus these four vertices v, w, x, y. So vertices adjacent, suppose number of vertices adjacent to v or w in S is m, and number of vertices adjacent to x, y in S, this is happening in G. Number of vertices adjacent to x, y in S, vertices adjacent to x, y in S in G is n. So so we see that degree of V plus degree of W, degree of V plus degree of W is m plus 2, because this m, so other than four vertices, suppose we have these other than four vertices, the degree contributed of V and W was m, and in G and what about these four vertices? So we see in G, V is attached to X, so we'll have a plus 1 coming from that, and W is attached to Y, so we'll have a plus 1 coming from Y. So, okay. Yeah. Is there a question? And if we look at, okay, I think, yeah. Okay. So, oh, I see. Okay, so sorry, I have exceeded the time today. Uh, So since time is up, maybe I'll complete last two problems next time. So like before going that, if you have any quick questions, you can ask.
Yes, ma'am. Like I
Yeah.
have small doubt in
Yes.
finding
Yes. Yes.
diameter of the
Yeah.
cycles. Like if the cycle is odd, what is the actual thing you see?
Okay. So yeah. Oh, sorry.
Cn. If n is odd,
Yeah. So diameter of Cn
yes,
when n is odd,
yes,
right?
yes,
This is your question, right?
yes, ma'am. Yes.
So suppose we have five vertices. So saw. Wait.
Yes, ma'am. You just.
Yeah, like we have already discussed this. Recall to. Okay, so something has happened to my screen. Wait. Okay. Sorry.
It was some problem we discussed, ma'am.
Yeah. Sorry, something has uh, only half of my screen is okay. Yeah. So diameter of odd cycle was coming out to be n plus one. Yeah.
N plus one.
Yeah.
Okay. Like, what if if you have two n plus one? If n is two, then it is C5, right? Then the diameter will be 3. No, I guess like diameter of C5 is 2, I guess. There's some confusion there.
Okay. So
What if
diameter of C5.
Three.
it's
Yeah.
3?
So see, diameter of C5, V1, V2, V3, V4. So, okay. So you're saying that diameter of C2n plus 1 should actually come out to be n.
Yes, yes, yes.
So if we, okay, so let's, so here, yeah, sorry. Yeah, you are right. So if we see this triangle case also, it is C3 is C2 into 1 plus 1. And here also diameter of C3 is 1. Because, yeah. So, and here also in C5, diameter, distance between V1, V4 is 2. And distance between V1, V2 is 1. And distance between V1, V3 is 2. So, yeah. So, if you have odd number of vertices, then the diameter of C2n plus 1 is coming out to be n.
So both for even and odd, it's like n, right?
Yeah, it's for even and odd, it's coming out to be n.
Yes.
Yeah. Thank you for correcting this. Yeah.
Yeah, thank you.
Yeah. So this is n. Any other questions?
Ma'am, I
Okay.
have a doubt in the assignment 2, second question, ma'am.
Uh, okay.
So if you have time means you can explain, ma'am.
Okay, if it
Otherwise, we
is,
can see it in the next class.
yeah. Okay, so assignment, yeah. Like, okay. Yes, we can, so we can discuss it in the next class then.
Okay,
Is
ma'am.
it?
That's a hypercube QK problem, ma'am.
Okay. Yeah. Yes, like we can discuss it in the next class now.
Ma'am, and one more thing, ma'am.
Hmm.
Can we get the live session videos in the as a YouTube link?
uh, yes, they were they were supposed to be provided to you. So like I think there's some so I'll tell them. So I uploaded the video, they just didn't provide the link. So yeah, it
Yes,
will
ma'am.
be
Because
I hmm,
yes, ma'am. Because in previous NPTEL courses, I have get that video in YouTube.
yes.
That's why I have asked now.
Yes. By this week you'll get those links, and you'll also get the notes also. Okay.
Okay, ma'am. Thank you, ma'am. Thank you.
Okay. Yes. So we'll meet next time. So
Yeah.
like there will be There will be an announcement.
Exam will be computer based or writing final.
Okay, I'm not sure about that, like how the exams, so how exams happen. But like, okay, uh, so I have an announcement. It will be announced later also. So the next week session will happen on this Tuesday, like day after tomorrow, instead of Sunday. So the next session will happen on the coming Tuesday.
At what time?
Same time, 5 to 7 p.m. There will be an announcement, like it will be announced by NPTL also, but I'm telling you in advance. So it will be on Tuesday, 5 to 7 p.m. That is just coming Tuesday. Okay, so I'll see you next time.
Is it not possible to keep on Thursday?
uh no, only for this time it will happen, only for this week it will happen on Tuesday. Otherwise it will happen as usual on Sunday from 5 to 7 p.m. Only for the next week it will happen on Tuesday.
Look, can you keep on Thursday? I'm telling you.
uh I no